So basically this is our DC generator, and you can see this is the nameplate of the DC generator. We have here different readings. We have here the voltage, and we have, this is basically the name, and this is the current ratings of the machine, power rating. Of course, we don't have power factor or frequency. We have the rated speed, 2040 and 1700 RPM. We have the field rated current and the field rated, field rated voltage and the field rated current. This is the nameplate of the machine, and we will fill a table later on. So basically, based on this nameplate, we are going to fill in the manual. We are going to fill this table 1, generator plate data. Okay, this will be filled based on that nameplate. Then we have generator winding resistances. So now we will start our experiment. Electrical energy. In real life, you will never drive a generator by a motor. There is no benefit of that. Electrical energy. So to do the
some flipping here. Was there any problem here, gentlemen?
All is good.
Okay.
We need to rotate this machine. We need a mechanical source. But since we are not using here, we don't have steam turbines or gas turbines or internal combustion engine, anything. We will use this machine as a motor. So this will run as a motor to rotate the generator for us. The purpose of this machine is to work as a motor. In real life, you will never drive a generator by a motor. There is no benefit of that. But we are using it as mechanical input for the generator. Okay, this is just because we don't have steam turbines or engines in the lab. So now we said we need to measure the speed, isn't it? You remember we said we will fix the speed. How we will measure the speed? We will use a device called tachometer. This device is connected to the shaft here between the motor and generator. So the speed of shaft is converted to electrical signal voltage proportional to the speed. As we increase the speed, this voltage will increase. How we will measure the speed? We will connect this tachometer to CASILab. You remember we said the CASILab, we can measure the voltage by CASILab software in the PC. So this CASILab will take this input voltage, and then we will do the CASILab setting to measure the speed. This is regarding the generator. And as we did before, so to do this experiment, what do we need? We need also DC supply, because this we will connect this as a DC motor. Okay, so we will need a DC supply to supply the motor. Okay, so this DC supply will be connected to this motor, and these DC terminals will be connected to the field of generator. You remember we said we will do separately excited DC generator, and we will do open circuit characteristics. For open circuit characteristics and separately excited DC generator, we will use this DC supply. But for the self-excited DC generator, will we use the supply? No. We will excite the field from itself. So the shunt compound and the differential cumulative compound, these types of generators, when we do the connection, we will not use the voltage for the field. But this supply is only to supply the motor. This is not related to our experiment. We will study the motor next lab. Is it clear? So to do this, we will measure the current and voltage as well, isn't it? So whatever load we connect to this generator, we will use basically this variable load. So this variable load will be used to do the load test, the load characteristic of DC generator, and then we will use, as we usually use, the CASILab, the isolation amplifier and the CASILab to measure the voltage and the current. So we will measure voltage, current in these channels. We will channel them to the CASILab device, and then to the CASILab software in the PC, and also we will measure the speed. Is it clear? And these are the fuses. We said any voltage supply we use, we have to pass it through the fuse. So all the power supplies, when we start using them, we will pass them through the fuse.
Okay, gentlemen, that was the initial video. Now the second video.
Doctor.
Yes.
When we will finish the experiment, because I have an exam.
Sorry?
When we will finish the experiment today?
Obviously, the official time is 6:10.
6:10.
Yes, official time is 3:30 to 6:10. We should utilize all the time, but sometimes the lab experiment is shorter, so we finish early. But maybe another two videos, I think 2 or 3. This is 7 minutes video, but we have 1 or 2 more videos finished. So I cannot say, because I don't know the next videos is for 10 minutes or 15 minutes, but officially we are allowed, we should go from 3:30 to 6:10. This is allocated time. Okay.
Okay.
We have to fix all problems inside the lab. So we have enough time, even big problem can be solved. But inshallah, we fixed all problems. No, there's no problem. We have 1 or 2 more videos, inshallah, we'll finish quickly. But please note that this time is up to 6:10. But we'll finish earlier, inshallah. So this is okay? Can you hear?
So as we said before, we are going to measure.
Can you hear, gentlemen? Can you see it?
Yes, Doctor, clear.
But okay.
Generator winding resistances are A1, A2, B1, B2, C1, C2, D1, D2, D1, D3, and so on. So let's measure this. So now we will come here. We will measure A1 to A2. Okay. We will measure the resistance. So basically this voltage is changing, the resistance here is changing. Why? I am rotating the shaft. This is changing because it is the resistance and these are connected to the brushes. So the position of the brush will affect this value. Okay, so now let me move this a little bit. So now we can see, we will take the smallest value. We can see it is 5 ohms. So A1, A2 is 5 ohms. Okay, so we will write here 5 ohms. Then we have B1, B2. So again, we will do the same. We will measure B1, B2. What is the value? 1.7 ohms. Okay, which is very small, 1.7 ohms. We have C1, C2. So B1, B2, C1, C2 are the armature windings.
Gentlemen,
2.5 ohms. We can see that the armature winding resistance.
Here, gentlemen, we are completing this table and procedure to calculate the resistance. You know, we have done many times. You just connect the multimeter to 2 terminals. It can give you the resistance. So we complete this table in front of you for one value. Rest, it is again the same procedure. So I'm just skipping little bit just to show you the next. Basically, between 2 terminals, just connect the multiple terminals and you find the resistance. So this is repetition of, so I'm just skipping this repetition just to save your time. So now you can see from here, you can see here that we have field 4 values.
The shunt field windings.
Now we can show you all like this, view this value.
So this is 676 ohms, very big number compared to the series field, 676.
You can see here, gentlemen, you can see here this point. We are just completing this table, but just connecting the 2 terminals. So if you allow me, I can skip this measurement part, this table. This table will be given to you, right? It's okay, gentlemen, or no?
Yes, sure, Doctor. Yes, Doctor, of course.
Okay. So I can just skip this measurement things and then you can see.
Table 4, and I will show it to you later. Is it clear? And table 1 and table 4.
You can see table 4. Also, we are measuring the resistances A1, A2. All these tables, the procedure to measure the resistances is exactly similar. Like we just connect 2 terminals across the 2 terminals of the machine. It will give you the value of the resistance. There is no like conceptual, like very big learning point. It's just connection multimeter. So I think I can, if you allow, I can skip this for you just to save your time. Or some people may be getting bored. So you can see just the filling the table.
So 20
here we're just
nominal
filling
speed.
the table, and you can see this one. This is important that you can see this is nameplate data of the machine from here. This is important. You can see this is
1040, 1700.
I can explain it to you verbally. I can say with myself that you can see in front of you we have a nameplate data of the machine. Nameplate means that every machine has a plate on it. This plate shows you certain things. Like this machine shows you the voltage value, the speed value, the torque value, and these things are rated value. You can see that we have 220 and 135. It means that this machine can work at 220 or it can work at 135. There are two options for this machine. So nameplate data means that this is the generator, it's the machine. So it means that it should have a voltage, it should have speed, it should have power. And we don't have power factor because this is DC machine. Similarly, we don't have frequency because frequency is 0 for this DC machine. So you can see that we are filling the table which is in your manual. You can open your manual and see it. And just filling the information from the nameplate of the machine, you can observe this.
To 135, it is supposed to work at 1700 RPM. At 220 volts, it's designed to work at 2040 RPM. So 20 nominal speed, 2040, 1700 RPM.
You can see here we have discussed, we have written the voltages, 220 volt and 132 options, 2040 and 1700. It means that 220 gives you 2040 voltage, 135 volt gives you 1700. It means that this machine is working at two voltage levels and two speed levels because voltage is directly proportional. Not directly, but voltage is increasing the speed. Okay, so you can see from here.
Now it says nominal armature and series windings. Look, we have here three currents. Unfortunately, the manufacturer in the nameplate did not specify clearly which one is which. But here, these are the armature and the series and the field and different winding currents. And we will write them down here, 4.8, 5.6. Usually this will be higher current and this will be part of the current. And if you have series, for example, series motor, or we have it cumulative compound and differential compound. So this is the numbers, we will just put them here. 4.8, 5.6 and 5.4. Then we need to nominal field current. This is the nominal field current for the shunt winding. And we said we have series winding and we have shunt. The shunt winding, it has nominal current of 0.24. So this is 0.24. Where is 0.24? Okay. And the nominal power in watts. What is the nominal power? Where is it? 0.7 kilowatt. In watts, it's 750. So we have 750 as a nominal power. Is it clear, Shabab? So basically this is part A. The same nameplate is for the motor because we said they are identical machines. We will fill this similarly. But for table 4, we have to do the measurements similar to what we did in table 2. I will fill it and show it to you later.
Okay, gentlemen.
Okay, Shabab. So now we will start doing our experiment. We will move to part B. It says generator open circuit characteristics. So for open circuit characteristic, this is our circuit. Basically in this circuit, as you can see, this is the motor. This is the tachometer. We said we are going to measure the speed, and this is the generator connection. For the open circuit characteristic, as you can remember, we are going to measure the field current and we are going to measure the open circuit voltage. How we will measure the field current? We will connect the field supply to a DC source and we will measure its current. So this is basically DC supply, and then it will go to the ammeter in the isolation amplifier, and it will come back to the field, sorry, this is, yeah, it will come back here to the field windings and it will continue like this. So this is the field circuit, and then we have the armature circuit, and the armature circuit, as you can see here, A1, A2, here this is the brushes, and these are the windings. The windings are after the brushes, but this is just for simplicity, a representation. So this is the first and the second armature windings. So these armature windings will go to UA and OA. OA is what is the negative part, and UA is the positive part. So basically this is a voltmeter and this is ammeter. Voltmeter is open circuit, ammeter is short circuit. So we are measuring the current of the field, and we are measuring the open circuit voltage, open circuit voltage of the armature circuit. Is it clear? So this is what we care about. this circuit is for motor. We will explain it in next lab. This is we are connecting here a shunt, self-excited shunt motor here, and this is tachometer. So basically tachometer will go to the CASI sensor, and again these measurements also will go to the CASI sensor. This is what we will implement right now. I will start with the motor. Basically in the motor we will have power supply, and we will have shunt windings, and we will have the armature windings, but don't worry, we will explain this in more details next lab. And then I will connect this. So I will start with the motor. Okay, I will do the connection for the motor, and then we will do it for the generator. So for the motor, first thing we are going to connect. We are going to use a DC supply. This is our DC supply, the positive of this DC supply. As we said before, any DC supply you have to pass it through the fuse first, then it will go continue to your circuit. This is our fuse. So after this it will go where? It will go to our machine. So after the fuse it will go to our machine, to the field windings here. Okay, the shunt field windings. And where does the negative part of the machine will go? It will go to the lower terminal of the field winding. So let's go ahead and do that. So this is basically the lower section will go to the negative part. Is it clear? So this is E1 and E2. This is E1 and E2. You can see it also here. This is E1 and this is E2. Okay. Now we are going to connect it to the armature circuit. This is a motor. Don't worry about it. You will understand why it is like this. So E1 will go to C1. So we can see here E1 will go to C1, and we are going to go from C2 to B1, isn't it? You can see here C2 will go to B1. So this is C2. This is going to go to B1, and B2 will go to A1. Will go to A1, and A2 will go to E2. Okay, A2 will go to E2. Okay, this is E2. You can see ya shabab. Sorry, this is E3. Sorry for this ya shabab. This is E3. We have to connect it to E2. Yani I took half of the windings. This is full. This is part. So from E1 to E2. This is the what we have to do, yani, or F1, F2. Is it clear? So we have this. All windings are connected. So now our motor is ready. If we turn on the power supply, the motor will start rotating. But we will not do that. We will do it after we connect our generator. So now, for the generator connection, we said we will have the generator connection again. A1 will go to B2, B1 to C2. How we will do this? We can understand this from this diagram here. From this diagram here, you know that these are the armature winding, and this is representing the brushes here, or the terminals here. So A1 will go to B2, and then from B1 supposed to go to C2, isn't it? B1 supposed to go to C2. So this is B1 is going to C2, and then from C2 we are going to measure the voltage. And from C2 it will go B1 to C2, and C1 will go to the voltmeter to measure the voltage. This is the voltmeter. So UA1 or UA. C2 will go to UA. Is it clear ya shabab? So this is the connection here, and then the negative part A2 will go to the negative part of the voltmeter. So this is the voltmeter. This is A2 is going to go to OA in the CASI, because now we are here measuring the voltage. To measure the voltage, you remember we said we will set this over 100. So whatever voltage we are measuring here, it will be divided by 100 to be represented here to the PC. We will continue that later, but now you know that this channel is used to measure the open circuit voltage And why we are measuring open circuit voltage? To determine the load characteristic. We are done with the armature circuit. So all this connection is for armature circuit. Now what we will connect here, we will connect the field circuit. We said we will connect the field circuit to a DC supply. Why we are going to connect it to DC supply? To vary IF. We want to have IF versus VT. We will vary and we want to see how this will go up. Is it clear? So now we are going to do this. We are going to connect to DC supply. So where is our DC supply? This is the DC supply. Another DC supply that we have. So this is DC positive. Again, any supply it should pass through the fuse first for protection. And then the other terminal. Okay, the other terminal of this will come where? It will go. So we are having a power supply, and then we are measuring the current. Sorry, we will first measure the current. After measuring the current, it will come back to the machine. So now, let's bring it back. I think this one is not. So now, after we measure the current here, this is the ammeter. It will pass through the ammeter, and then it will come back to the machine, as you can see in E1. So E1 is the positive terminal, or the positive terminal of the field, and then from E2 it will go where? To the negative terminal of the power supply. Is it clear? Basically we connected power supply, DC supply, to an ammeter. Again, as you can remember, when we use this as an ammeter, this channel, we will select here 1 volt per ampere. What does that mean? Each 1 ampere passing here, it will be represented as 1 volt here. And 1 volt here representing 1 ampere here. This is the isolation amplifier. This isolation amplifier will be connected to CASI sensor and so on. Is it clear, ya shabab? Is it clear? So now basically this is our connection. Now we are done with the main circuit connection. Now we are going to do the sensor connection. And whatever we are going to acquire, we are going to measure it using CASI sensor. So first thing, as we said before, first thing we are measuring here is what? The voltage, isn't it? The voltage is here in channel 1. Let's connect it here to UA1. Let's connect, for example, the current to UB1. Okay. How we know this is UA1, UB1? You remember it, and we can see it in the CASI Lab software very soon. So this is 1, this is 2. Any voltage measurement, it should be referred to some reference. There is no, you should use 2 terminals. And this is a voltage, it is with respect to what? All these channels are with respect to this neutral. So this is the common neutral for all channels. This neutral will go here. So this will represent all of them. Okay? So this is for voltage. Now what's remaining? We have the open circuit voltage, we have the field current here. What is remaining? The remaining is the speed. You remember we said we will measure the speed for this machine. So the speed is connected here to which channel? To UA2. So we will connect this to UA2. Let's connect it right now. So the tachometer, as we said, tachometer will have very small voltage. We don't need to use the isolation amplifier with the tachometer. We can just use the tachometer. We can just connect it directly to the CASI sensor. So this is the tachometer. This is UA2. And again, the neutral is connected to the neutral here. Again, we said any measurement will have, you need two terminals to measure a voltage. So this signal will be voltage signal representing the speed. Is it clear, ya shabab? Is it clear?
Okay, gentlemen. Circuit is connected. Now we'll go towards CASI.
Shabab, now we will do the CASI Lab setting. As you remember, first thing we do in the CASI Lab setting, we are configuring here the CASI Lab software and the sensor. So this device is representing the sensor here. You can see it is a similar shape here. The sensor, so we are using this channel, and this channel, UA1, UB1 and UA2. What is UA1? We said voltage, this is current, field current, and this is the speed. So now let's do that. So here Let's start with UA1. It is a voltage signal. We measure average RMS. What do you select? Do we select average or RMS? We will select average because the measurements that we are going to take is DC, because we have DC current, DC output voltage, and also the speed is represented as a DC voltage. The speed, the tachometer will give me DC output voltage proportional to the speed. So this is average. This is 1. This is UB1. We said we connected UB1 to what? To the field current. Again, it is average values. Then UA2. This is called UA2. This is how you know the name. And you can see it from the, you can compare this to the hardware connection to know where you are connecting. So this is voltage, again, average values. Why? Because this voltage is representing the speed in what? The speed of the generator from the tachometer. So here we have UA1, you have UB1 and UA2. UB1 is current, isn't it? But why it says voltage? Because the CASILAB can measure only voltage. That's why in the isolation amplifier we said 1 volt per ampere. And 1 ampere here is passing will be converted to 1 volts. But we know that it is current here. This is what we will do next. So we did the setup here. Now we will define the parameter as we do usually. We will select a quantity, new quantity. What is the first thing? We are measuring no load voltage. What is the formula for the voltage? We said UA1, isn't it? Because we connected to UA1. I will multiply by 100. Why by 100? Because here I selected in the isolation amplifier to divide the voltage for me over by 100 to isolate the high voltage circuit from the low voltage circuit. So multiplying this signal by 100 will return for me the original signal. What is the symbol for this? Let's call it EA. Unit is volts, and range, let's say we will expect up to, for example, 300 decimal, 1 decimal place. This is no load voltage. This is field current. Let's define the field current. What is the formula for the field current? It is UB1. UB1 is the field current. From where we get this UB1? We know that we connected to UB1 the field current. The symbol will be I underscore F. Unit is amps. From 0, do we expect 100 amps? No, we expect very small current. So let's say 0.4. Since the numbers are small here, decimal places, we will make it more. We will make it 4 decimal places, for example. Because the numbers are small, we want to see all the numbers. This is field current. We are done. Now another third quantity, speed. Okay? We will define the speed. So what is the formula for the speed? It is UA2, isn't it? We connect to UA2. But what is the factor that we will multiply by? We will multiply by 1000. If we multiply by 1000, the tachometer will give us the speed in RPM. Yani if the tachometer measures 1 volt, it means 1000 RPM is the speed. So what is the symbol? Let's call it N. Mechanical speed. RPM. The unit is RPM. We expect the range to be from 0 to, let's say, 2100 RPM, and decimal place is 1 decimal. Is it clear, ya shabab? So now we did all these settings and we are ready to take our measurements. So for all the open circuit characteristics, this is the setting is ready. I will close this. This is the raw data. I will close it. I will show whatever I measure. This is IF. This is what I defined. EA is really what I defined. RPM is what I defined. Okay. So this is what you can see here. And again, this will be manual recording. I will select manual recording. I will close. So now my CASILAB is ready.
Okay, gentlemen, now we're ready to take the readings. Okay, we have done the CASI. Now the read. We have 1 or 2 more short videos, inshallah. We'll finish before our actual time of 6:10. So we'll finish well ahead of time, inshallah. So this is now we are taking the recording of data. We have done circuits, we have done CASI. Now we are taking the data for this open circuit test. Oh, no, sorry,
Okay.
open circuit characteristics basically.
Now our CASI lab setting is ready, our connection is ready. We can start our experiment. What do? We will start by rotating the generator. How we will rotate the generator? Using the motor as we discussed before. So basically we have a DC motor, so we will turn on the DC supply. We will start increasing the voltage. So we are not testing the motor here today. We will explain it next lab. This is just as mechanical power representing the mechanical input power for our experiment. I am increasing the voltage here, and I am measuring the speed. As you can see here, what is the speed? 1600 RPM. I will increase the speed, increase it. Okay. Until let's say 1900 RPM. Around 1900 RPM. So I will do the test on 1900. We said we will do the open circuit characteristic at fixed speed. What is the fixed speed that we will use? We will use 1900 RPM. We are supposed to use 2040, but the machines are old and they cannot handle that speed now. We will reduce it a little bit. We will work on 1900 RPM. Is it clear, ya shabab? So at 1900 RPM, what is the open circuit voltage? There is 5 volts. From where does this 5 volts come from? From the residual flux in the machine. There is no field. The field windings, there is no field current yet, but we have still voltage because of residual flux. What is IF? It is 0. So now I will start applying field current. Okay? I will take one measurement now by pressing F9. This is one measurement taken. Okay? So let me show here EA and IF, EA. Just a second, ya shabab. I will remove, because it's displaying UA2. I don't want to show this. We want our x-axis what field current, and our y-axis what voltage, isn't it? So all are off. All are off. We want x-axis field current, y-axis EA, or the open circuit voltage. So now I took one measurement. It's at 5 volts. Or sorry, I don't. At 5 volts. Now I will turn on the DC supply, which is supplying the field. Now the current here is 0. Everything is 0. I will start increasing the field current. What do you expect when I start increasing the field current? You expect the voltage to increase, isn't it? So now let me see. I am now increasing the field current. Do you see the voltage is going up? You see it is now 10 volts. Can you see? Because I turned on this supply and I am increasing the field current. Now I will take one measurement. This is one measurement. Now I will continue increasing the field current and taking measurements. This is another measurement, and so on. I am continuing taking there is issue. Okay. So I am increasing the field current and taking measurements. As you can see, ya shabab, until where I will go. I will go up to IF equal 0.24 amperes, which is the rated field current. So I will just continue. Okay, shabab. So I reached IF equal 0.24, and this is the terminal voltage at this rated field current. We are expecting 220 volts, but again, because of the machines are a little bit old and they are affected with time, and also we are testing at lower speed. We are not testing at 2040 RPM. So this speed should be maintained constant. But in this experiment it was varying a little bit, but that's okay. So you can see the linear behavior. Do you see this curve? It did not saturate. Why it did not saturate? We explained before that this is because the reluctance of air gap is constant and it is dominant on the reluctance of the core. The core is saturating, but it is not. It does not affect that much as compared to the air gap, because the air gap will have very big reluctance. Is it clear, ya shabab? This is IF and this is EF. So we are measuring the open circuit voltage versus IF. This is the open circuit characteristics, and we can call it magnetic characteristics of the DC generators.
Okay, gentlemen, here I have to stop for some time, maybe 1-2 minutes, just to discuss something. Gentlemen, did you understand this is the generation of the generator? Can you understand what I was discussing in my class, that we have EA equal to K phi omega? Do you remember this? The people are here, like I have, for example, Ali Moshel is here.
Yes, sir.
Ali, see here, we were discussing in class that the generator action is that EA equal to K phi omega. You can see that EA is here in the middle. You can see in this video picture, you can see EA 174, whatever, equal to K is the machine constant, which is the machine over machine. Phi is coming because of this field current. I discussed with you that once the current is flowing, field current is flowing in the circuit, a flux is present. It means that field current represents the flux. It means EA into K into phi. This N is RPM, but we have discussed omega. This is same thing. Omega and N is the same thing, just we are expressing here in RPM, but normally omega is expressed in radian per second. It means that this is speed. So it means that we are verifying today the generation of the generator voltage. So this is generation part, where you can see on x-axis we are changing the field current, means that we are changing the flux, and y-axis we are changing the voltage. You can see that flux and field current is directly proportional to the production of EA. From where we verify this information? EA equal to K phi omega. If the omega is fixed, obviously which is fixed 1970 here, K is also fixed. We are changing only field current, which is changing flux. It means that EA is proportional to flux, which is in fact IF, and that very basically verifies the linear characteristics of this machine. IF versus EA, which is generation of the generator. But it can saturate at the end because this is magnetization characteristics. It can saturate if you increase further because machine has some limitation. But in general, our relation between flux and the production of E, which is voltage, is directly proportional, which is verified in this experiment. Okay, so once this generation is verified and characteristics are verified, generation characteristics, next part of experiment shows you the terminal characteristics, where we'll have the voltage generation, then we with load the voltage drops down, and we'll show you two characteristics, the shunt generator and the cumulative compound generator, inshallah. Okay, so this is the physical actual relation with the theory. So I am now showing you the second, the other. We have not too many videos, 1 or 2 more videos, inshallah, then we'll end, inshallah. So please be careful and attentive, because these are very important understandings. Okay.
Okay, Shabab. So now we are done with that. We are done with this separately excited. Now, separately excited, we said we have a DC supply.
Doctor, I can't see.
Separately excited.
Sorry?
I can't see. I don't know why.
Okay. No, I'm just.
You didn't change the screen, doctor.
Sorry?
You didn't change the screen.
Okay. I'm sharing. I'm sorry. I didn't see the. It's not sharing. Eh? Okay, I'm showing you. Just showing you. So.
Excited, which is shunt, very common type. Shunt, we will connect the field windings.
Can you see the gentleman or no? Can
Yes,
watch
we
it?
can.
Yes.
Now we are discussing the shunt generator characteristics. We have only 2 characteristics in this lab experiment. One is if you see your manual, I have opened a different manual by mistake here. So it is same information. So DC shunt generator and cumulative compound, the two generators only. So we have one or two more videos, and that will end our experiment. Please watch it carefully.
Shunt field windings to the load. E2 is connected to the load. In the separately excited, it was connected to separate power supply. Now, the generator will excite itself. The armature terminals will be connected to the.
We have another supply. Now we're discussing self-excited. Now you can see that there is no additional power supply. We are just giving the voltage directly from the production back to the field circuit as well. So this is known as shunt self-excited generator.
Shunt field windings like this, and this will be parallel with the load. So this is what we will do. Basically, what we will do, we will disconnect the power supply and connect E1 to C1, E2 to A2. Is it clear? E2 will go to A2, E1 will go to C1. But now these two are connected to power supply. We will just disconnect them. You can see here, this is E1, this is E2. I am disconnecting E1 and E2. They are open circuit, okay? I have to remove the cables from here and there, okay? I'm disconnecting the power supply. And also the fuse is no longer needed, okay? This is the fuse. So now I am disconnecting the power supply. خلاص. We don't have power supply for the field windings, isn't it يا شباب? This is for the motor, we don't care about this. But for the generator now it will excite itself. It will excite itself, okay? So now, as we said before, E1 will go where? Here. E1 will go to C1 or to the load, isn't it? Where is C1? E1 will go to C1. This is C1. And E2 will go to A2. This is A2. Now the field is excited from itself. We can see the armature is connected to the field. Now we will see how it will look like. Is it clear, ya shabab? So now we will see how it will look like.
Now you can see
okay.
Here you can see the characteristics here. Let me stop. Can you see this, gentlemen? I will show you something here. You can see that this graph, which you can see this line which is going down. You will see in Cassie, once you get the file, you'll see that this file with this line which is going from here down. You can see it going down here. So this video maybe is the right corner is not visible to you, but this line which is going down, it shows you the terminal characteristics of the generator. This is what we discussed. Okay. In your, once you get the Cassie files, you can increase the scale of vertical axis. Then you can further see proper, very, very clear shape of this this picture. Okay.
Okay. This is one measurement. Now I will start increasing the load current, this load current, and taking measurements. Increasing the load current, taking measurements. Increasing the load current by reducing RL, taking measurements, and so on.
Starting from this point, and once we are increasing the load, means that load current is increasing. Like load is increasing, this is going down. This is because of IR loss. You can see here.
I am doing the same, repeating the same thing, and I am observing that the load is reducing. Can you see, ya shabab? Okay, do you see a shabab here? I will change the, I will make maximum 2 amps. Okay, and here I will make maximum 200.
Just that voltage is going down like this. And this last 1 or 2 reading, you can delete these readings because these are just maybe noise coming back. But here up to here, your graph is enough. Okay, So gentlemen, this is the one characteristic of the generator, which is I have discussed in class that we have this is the starting point. Because of load, this is going down, and you can delete last the 1 or 2 readings because this is just a noise. At the end, maybe it's going back. It should not go back because this is reducing. It should not go back, but this is maybe last reading from here, left hand column, table, left hand table. You can delete the last measurement, which is basically a noise. Okay, thank you very much. So do you have any questions, gentlemen, so far in self-excited DC generator? Do you have any question? No question?
Thank you, Doctor.
Gentlemen, are you here? Okay. So inshallah, we have very few more minutes to basically go for cumulative compound. And in cumulative compound, obviously, we'll connect series and shunt windings together, as I discussed in my today's class. That in cumulative compound, we have shunt winding, we have series winding together. And I have explained in detail that the shunt and series combined together gives us cumulative compound generator. Okay, now we are discussing it.
Okay, Shabab, so we are done with the shunt motor. Now what we will do, we will connect it as a compound.
there is no video.
We have community compound and we have the first one. So
Yeah, Doctor, you didn't share the video.
Sorry?
You didn't share the video.
It is shared, gentlemen. It's not shared. It's
No.
shared. Let me do it again. It maybe always ask me to do it twice. I don't know why. Let me do it again. So it should continue, but I don't know why. Okay.
Yeah, now it's okay.
It's okay? Okay.
It's shared there.
Cumulative compound, basically, this is the shunt. Cumulative compound, we will add a cumulative windings in series
now
with the
you can
load.
see here that what is the difference between the previous and this one? It is very extremely simple circuit that this was shunt before. You can see figure number, not this is figure number 3, not 4. Previous figure 2, figure 3. So you can see that in figure 2, this winding was not present, and everything else is the same. In this cumulative compound, we are adding only one resistor, series resistor, which is D1 and D2. From shunt to compound, there is only one resistor that is added, and it becomes a cumulative or compound generator. Now you can see that we're just adding one resistor here. So this E1, E2 is shunt resistor, D1, D2 is series resistor. Because of these two resistors together, we call this generator as a compound generator. So this is the only difference. And normally we ask this question in our oral test and experimental test, that if we have shunt generator, how can we convert it to cumulative compound or compound generator? Your answer is simple, that we have to add only one series resistance that will convert this shunt generator to compound generator.
Come again,
So
Doctor,
this
can you
is the
repeat
only
it again?
Sorry?
Can you repeat it again? If we have what?
Yes. We are saying that we discussed the shunt generator in the previous part, where we have only this winding, which is E1 to E2. D1 but D2 was not present. Okay, that was a shunt generator. Now, in order to convert a shunt generator to cumulative compound generator, I need only one series resistance, which is D1 to D2. This D1, D2 only in the previous circuit can convert a shunt generator to cumulative compound generator. So it means that this D1, D2 is the change in the previous circuit. Exactly same circuit, only change is D1, D2. So my answer to the question is that we can convert a shunt generator into a compound generator if we add a series resistance at the output of the generator, which is here, D1, D2. Okay, understand, gentlemen? And obviously,
Yes.
in our class today, we discussed that in order to make a compound generator, we need one series resistance here, which I am pointing here. We need a parallel resistor with shunt resistor. So series and shunt together like D1, D2 and E1, E2, we can make a cumulative compound generator, which is there in the diagram. You can compare two diagrams in your manual. If you open your manual, you can see figure 2 and figure 3 in your manual. Both figures are the same. Everything is same except D1, D2 in figure number 3 in your manual. Okay.
Series with the load, and basically the load current will be will equal to the cumulative compound field current, okay, or the series part of the field current. So basically E1, C1 and D1 will be connected together, and from D2 we will measure the current. Okay, so here
Here just check one connection.
so now you can see, Shabab, here E1, instead of it going to measure the current, it will go, E1 will go to the D1, and from D2 we will measure the current. This will go to the ammeter, D2 will go to the ammeter, and E1, D1 and C1 will be connected together like this. That's it. This is the cumulative compound. We have the shunt windings and we have the series windings together. What did we say? We expect the cumulative compound plot to be, it will have higher voltage than the shunt. So now what we will do, we will append new measurement series. Okay, append new. So we will start first of all. Let's start the DC supply. We will go to the same speed. 1900 RPM. You can see the voltage is high compared to the shunt. So now here we will say in this measurement, manual recording, we will here click append new measurement series because we want the other plot on top of this. Okay, append new measurement series, close. I will take one measurement now at small voltage. Let me increase the scale because now we have higher voltages, 250. Okay, so this is one measurement. Now, as we did before, we will increase the load current and measure the voltage. At 9, I am doing the same. Can you see, ya Shabab? The cumulative compound, the plot is above the shunt winding. Now we can increase this one until, let's make it 5. Sorry, 5. Can you see here? It still can handle more current. We will still increase the current, this one. So we went until 4.8 amperes. The speed here was decreasing. Practically we should maintain the speed constant, but it was a little bit decreasing, but that's fine now. That's okay for this for our test. Can you see? This is cumulative, this is shunt. Shunt the voltage will collapse faster than the cumulative, because in the cumulative, as we increase the current of the load, we have more field current.
Okay, gentlemen. So that basically ends our experiment, which is, you can see that this red color is cumulative compound and this black color is shunt generator. So in your lab, if you open your lab manual, we have three graphs. One graph is between IF, this first part, IF versus EA, which is straight line. The second graph is shunt, your part C, which is your shunt generator, which is this characteristic. Basically, this is very sharp characteristic as compared to cumulative. This red color is the cumulative compound lower characteristics of DC generator. Now you can see the characteristics that the general trend is the same, that every time we have a generation with the load, the voltage drops. But in shunt generator, the curve is more steep as compared with cumulative compound. And that basically ends our experiment today. So now you can understand in your oral test or exam, final exam, normally we ask this question that about these characteristics, because you are watching these characteristics. We can see that which one is sharper, So you can immediately can understand that the shunt generator is more characteristic. The slope is sharper than the cumulative compound. It means that cumulative compounds are above the shunt generator characteristic. You can see here. So these things you must understand that what is the difference between shunt generator characteristics and what is the difference between cumulative and shunt both. Understand? So sometimes we give you data, like we give you two graphs, and we can say that identify which one is shunt generator, which is cumulative compound. So obviously, very immediately, you can say that the top curve is cumulative compound and bottom curve is shunt because of characteristics. Okay. So inshallah, we'll give you two CASI files. One is for part A, which is generation, and we'll give you another file which for B and C, which is shunt generator and cumulative compound generator. You can plot them together. You can plot them separately. There's no matter. So we'll give you data for both, inshallah. You can use Excel. You can use CASI. Plot them together. Plot them separately. Discuss them together. Discuss them separately. It's up to you. So that basically ends our experiment. And if you have any questions, please ask. Please ask questions so that